5-2, day one free lesson. Hold your hats. There's a lot about to come at you. But they're all, well, 90% is based on these two little rules that you've been taught in Algebra 1, and you had to use them probably every now and then in geometry. But so here it is. X squared times x cubed. What does that even equal? Well, if you remember your rules, repeat after me. When the bases are the same, when the bases are the same, and you're multiplying, you add the exponent. So it's x to the fifth. So hopefully that rubs a couple brain cells together for you again. Go into that archive of memory. But now we got this problem where there's actually numbers. And I know a lot of students, you would look at 3 times 3 and the number 9 would pop into your head. Then you would add these and you would wonder if that's correct. Well, let's take a look at it, okay? 3 squared is 9. 3 cubed is 27. 9 times 20 is 180. 63, 243 would be my answer if I actually calculated this all out. Now, which one of these do you think equals 243? 9 to the fifth, there's just no way. That's a massive number. So remember, on this little example, there's a hidden rule. The base did not change. So you just keep the base. So when I see common bases, you keep the base the same. The only thing you do is you add the exponent. So that would be my answer. Or I could calculate it out to 243. Okay, keep that in mind. Next rule. When you raise a power to a power like this, what do? Well, the rule is you multiply. When are you going to have to use that rule? Every now and then. It just pops up. You got to be on the hunt for it. So I don't add in this situation. I multiply. How am I going to apply that to an actual math problem? Right here. So there is an invisible 1 right here. Remember, chop down one tree at a time. Here I have a power to a power. 1 times 1/3 is 1/3. But now I look at this x to the 1/2 to the 1/3. I got to multiply these two together. So 1/2 times 1/3 is 1/6. So I get x to the 1/6. Now, look at that thing. 8 to the 1/3 power is the same thing as the cubic root of 8, which is 2. This is the same thing as, remember, that's my index, 6th root of x to the first power. You can put a 1 in there or not. But this is called simplest radical form of that math problem. So we got to know how to get from here to here. Now this is on the simple end of things, but we'll ease our way into it. Let's look at this one. Look, common bases, and we're multiplying. The base does not change. What do? What's the rule? The rule is right here. You add the exponents. Don't multiply them, because we don't have that situation. We have this situation, which represents this situation. So we add the exponents. So that they just make your lives a little complex. So they give you fractions instead of nice little whole numbers. So all I got to be able to do is add those. So, all right, well, I got to have common denominators. So negative 1/3 is the same thing as negative 2/6. And that's 3/6. But don't forget, that's my power. So this is equal to 81 to the 3/6. Well, we might as well reduce that right now to the 1/2 power. And that should be like, wait a minute, we've worked with these. That's the same thing as the square root of 81. Remember, that's my index. So there's a little invisible 2 there. Yes, there's an invisible 1 here, but what's the square root of 81? 9. And they start letting go of that thing where you have to put negative 9. We're just going to go with that. So that's phase 1. Watch it again if I lost you at all. Then they give us kind of vague, general, abstract problems with just letters. And that can be really frustrating. Now you got to just lock into your rule. Well, remember, if they tell you, take this radical form, write it in exponential form, we need to see those exponents. Remember, there's an invisible 1 here, invisible 1 here. We put the power over the index. This thing just slides over. So it's 1 over n. Do the same thing with b, 1 over n. And yeah, then the book might, and this is kind of weird, I think you should be done, but the book might just write it as the nth root of a times the nth root of b, which doesn't make sense to me because it's really just the same thing over here where you would have just split it up, and that's okay too. So I like this as the answer because it's forcing me to practice the rule that I've been hitting you with. So that's kind of a weird problem. Like, what's the answer? What do they even want? Mess around with it. Try your rules. See if it matches the homework answer. So now we're going to take a look at this before we look at one of your sample problems. Because if you don't know the basic rules here, it's going to be really hard to kind of figure this out. So let's take a look at this. First of all, I'm experimenting with this. The square root of 4, we know is 2. The square root of 25, we know is 5. The square root of 100, we know is 10. So first of all, is this a true sentence? And the answer is yes. But what am I trying to explain to you? I'm trying to explain to you that if you have the same indexes in your radicals, you can multiply the stuff underneath, because 4 times 25 is 100. But that's only one rule. You can also take one square root and break it up into the product of two numbers. Now I could have made it the square root of 5 times the square root of 20, but I wanted you to concentrate on the perfect square root parts just so things kind of jump out at you. So rule number 1, if they have the common index, you can multiply the stuff underneath. Now let's take that rule to this problem. We got a 5, we got a 5. They're the same index. That means I can multiply the stuff underneath. Now before I did that, I would actually ask myself, is there a perfect fifth root of 16? No. 8? No. There's a perfect cubic root here, but no. So what we're asked to do here is remember this rule and say, aha, I'm going to multiply these together. So 8 times 10 is 80, plus 48 is 128. And I'm done, right? No, that's why this stuff's going to get a little bit more tricky. So when I said you could take a square root and break it up into 2, they want your answer in simplest form. Now this is not simplest form. You did good by getting here. Now you got to go up the ladder and say, okay, the fifth root, is there a perfect fifth root of 128? If there is, it's probably 2. So let's take a look at the 2's and just stack a whole bunch of them together. That's 4, 8, 16, 32, 64, 128. Well, there's 1, 2, 3, 4, 5, 6, excuse me, 1, 2, 3, 4, 5, 6, 7 of these. I want to know the perfect fifth root. Well, that doesn't exist. So notice, look at this. 2 times 2 is 4. Let me pause a second. We better take a look at something like the square root of 28. Okay, you've done these before. Now, if we break this down, what you're supposed to do is pick the largest perfect square root that's a factor of 28. That'd be 4. Now, how many times is 4 going to 28? 7. So I go, aha, that'd be 2 square root of 7. If I take that thought, this is old stuff review, apply it to some more challenging stuff. What is the largest perfect fifth root that goes into 128? Now watch this. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32, 32 times 2 is 64. So look, 1, 2, 3, 4, 5. I want the perfect largest fifth root. So 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32. So 32 is my largest perfect fifth root that goes into 128. Now how many times? 32 times what is 128? Well, that would be 4. And then I think to myself, aha, what's the fifth root of 32? 2. Fifth roots of 4. Now you're going to get used to this, but I'm going to call this OIL, and I'm going to call this water, because some of you need to know oil and water don't mix. This is a radical, this is not. Can I go 2 times 4? I'm going to show you something. 2 times the square root of 25. Okay? Well, what's the square root of 25? Well, the square root of 25 is 5. So 2 times 5 is 10. That's the correct answer, but let's experiment. What if I did multiply these together? I'd get the square root of 50. Is the square root of 50 10? No, the square root of 100 is. So you cannot multiply these together because this is oil and this is water. So no. All right, so back to here. Am I done? Yes, because this is simplified and this is simplified. All right, that's a tough little problem. And there's going to be more coming at you like that. Pre-lesson's a long one. It's probably going to be a part 2 to this doozy. So, got about 5 minutes left in this video. Let's attack this one. So we got this messy stuff in here, all raised to the 1/2 power. Remember the rule, x squared cubed is x to the 6th. We multiply these powers. But chop down one tree at a time. So this is really the same thing as there's a 1 there and a 1 there, which there is, and I follow this rule. I've got this number land, I call it number land, but the rule is 1 times 1/2 is 1/2. Now I got the c, 14 times 1/2 is c to the 7th. Now I got this 1 times 1/2, 81 to the 1/2. Then I go 18 times 1/2 is 9. Am I done? Well, you should be recognizing that that's the same thing as the square root of 16, and that's the same thing as the square root of 81. So to simplify this, I get 4c to the 7th over 9d to the 9th. So problems are getting messier. You got to know which rule to use, what rule not to use. I didn't erase this one because I want you to understand this is a different rule than this one. This one, we got power to a power, power to a power. That's why we use that rule. This one, if you look at it, you're like, wait a minute, I don't have anything here. There's actually a 1 there, and there's a 1 there. So really, multiplying the powers is not going to change the problem. So what's this asking me to do? Multiply. This is going to force us to remember this rule, where you add the exponents if the bases are the same. But don't be confused. This is just your good old-fashioned 4 times 3. Don't panic there. That's just 12. These rules apply when the bases have these exponents like this, and the bases are the same. So I go, okay, I got x, and now I got to add 1/3 to 1/3, and I get 2/3. I got to check something to see if they want it. If they say leave your answer in I'll just tell you. If they say leave your answer in exponential form, you're done. If they say leave it in simplest radical form, you got to have a radical in your answer. So this would be 12. This is my index. Cubic roots of x squared, and that would be my answer in simplest radical form. This is simplest exponential form. So you also have to pay attention to their instructions. Next problem. So there's a basic rule in good old algebra. You're never supposed to leave a radical in the denominator. And if you recall, back in the day, you'd go, I'm going to get that out of there by multiplying square root of 2, whatever's in the bottom, multiply it by itself. So then the square root of 2 times square root of 2 is the square root of 4, which is just 2. And then you got oil and water, square root of 2. So you see this is the simplified version of this with the radical out of the denominator. So we look at this problem, and what is this problem really asking? Well, first of all, this is the same thing as the cubic root of 2 all over the cubic root of 27m cubed. So we got a problem. We don't care about this. It's okay to have a radical in the numerator. We got to focus on the denominator. Now look at this little gift. I did this one on purpose. There's a perfect cubic root there. Now the top, we don't care about. The bottom, what's the cubic root of 27? 3. Now look at this one. If I look at this and I go, I'm going to remember my rule, power over the index. That just takes care of it.